Good morning, Professor.
Good morning. Let's see, it's about time. Today I'm supposed to do a review. So before I get started, does anyone of you have any questions that you might like to ask me before receive exam 3 after this lecture? Let me see what did. Okay. Any questions before I get started? If not, let me go on and do my review. Let me see. I need to share the screen. And I'm going to I think a good way for me to do the review is actually to go through the previous lectures rather quickly. And if I go through the previous lectures rather quickly, then if you catch any important topics that you like me to emphasize on, I'll be happy to do them. Otherwise, let me just go through the PPT slides quickly. Okay, I guess in lecture 21 is when we start to talk about resonators. That was after exam 2. After exam 2, we started to talk about resonators, and these were the topics for that lecture in particular. So resonance behaviors are very important in circuits and electromagnetics, especially in electrical engineering. Of course, you would find that in mechanical engineering as well, in physics as well, but it is also very important for electrical engineering. And you can make a very simple circuit resonator using LC tank circuit and find that the resonance frequency to be that. And you can use the LC tank circuit as a filter. Say if you put this in between the voltage source and the load, and when you hit the resonance of this LC tank circuit, this becomes an open circuit. It becomes an open circuit and allows power transfer between the source and the load. And if you operate at other frequencies, this is not a very good open circuit anymore. So resonators are good filters. And you can make a resonator out of transmission lines quite easily by terminating the transmission line with the source load as well as the load, okay? And then there will be two different reflection coefficients between the two ends, and the wave can bounce back and forth between the two ends, making it into a resonator. And so we can first start by taking a transmission line model of resonator. It can be a waveguide if you have open circuit at this end and open circuit at that end, as well as a cylindrical waveguide. You can approximately model the waveguide as transmission lines terminated with open circuits. And then you can also even model a complicated microstrip line like this, where you have a ground plane, a microstrip line, and then you have open circuits at both ends. And you can see probably that in this case, you will have to put in fringing field capacitances at both ends. And so the reflection coefficients are not exactly 1. And you will have to write the transverse resonance condition using this formula. And you can work out the reflection coefficient at the load end and the source end. For these two particular cases, they will be plus or minus 1, depending on whether you have short and open circuit. And since we have open circuits, for them, they are both plus 1, and this would be your resonance condition. Okay, and if you have short circuits in one of them, this would be your resonance condition, and you can work out the resonance frequency of these structures quite easily. Okay, so you can actually sketch for intuition the current distribution on the open circuit transmission line. The currents have to be 0 at both ends. Okay, so the currents will look like this, and this is the lowest mode where you have half a wavelength, and this is the higher order mode where you can fit the full wavelength, and you can fit the 1.5 wavelengths over here. And however, if you have open circuit at one end and short circuit at the other end, you will have a I guess a maximum current at this end and 0 current at the other end. And if you sketch the currents, they will look something like this. Okay, I think this figure is not very good. This should be more oscillations in between. I just drew this figure wrong. Okay, so you can sketch the current and the voltage of the open circuit transmission line, and it will look something like this. And in actual fact, in the open end, you never have a perfect open circuit in microwave engineering and electromagnetic engineering. You will have to approximate the open circuit with a fringing field capacitance. Then only you can work out the resonance frequency of this structure quite well. And then you can generalize this concept to rectangular waveguides where you put the short at one end and then an open at the other end. And if you were to look for the guidance condition, you would model this with the transmission line with the correct beta z, and you can actually work out your beta z to be something like this. And you can actually get the resonance frequency of this rectangular waveguide resonator quite easily using this guidance condition or resonance condition. Then the important thing is that when you have an ODE, okay, when you have an ODE, and when you don't have a driving source on the right-hand side, you can still have a solution to this equation. Those are called a homogeneous solution and the natural solutions. And you will have to put boundary conditions at the two ends of a transmission line, for instance. And you can find the natural solutions to be occurring when beta times L is 2n pi and so on. And these are 1D resonators, and you can make them out of transmission lines quite easily. And then you can actually make them into 3D by using a cavity resonator. And you can have cases where the beta z equal to 0. Okay, beta z equal to 0 means p equal to 0. And then you can have a resonator where the magnetic field is a constant. And this is not possible unless you have open waveguide at both ends, because you know at the metallic surface, the normal component of the magnetic field has to be 0. So this picture is wrong unless you put open circuit and open waveguides at the two ends of the thing. And then if you have a rectangular cavity where you have shorts at both ends, okay, you can put shorts at both ends, then your beta z will be m pi over p. I think this should be a p instead of a b. I used p in the lecture note. Oh, sorry, it's d. P pi over d. M pi over a, m pi over b divided by p pi over d. Okay, those are the three discretized values of beta z, beta x, and beta y. And then you have this to be your resonance condition. If A is larger than B is larger than D, you will find that the TM110 mode is the mode with this being the smallest number. If this is the smallest number, then the resonance frequency will be at its lowest, okay? So you can actually go and look at these modes, and the field distribution of the TM110 mode would look something like this. This is the TM110 mode with the sketch of the electric field and the magnetic field. Magnetic field is going around like that. And there will be a take-home exam on this cavity problem in your take-home exam as you will receive today. And I have formulated that problem last night. Okay, so let me see. Okay, I'm looking. Okay, I get my screen back. So you can have a circular waveguide, the same thing happens. You can put open circuit at both ends or short circuits at both ends, and then you can get the resonance conditions. And you can use this kind of structure to make an antenna. If you make this into a cavity, and at the resonance frequency of the cavity, you can build up very strong electromagnetic field inside this cavity. And if you open a small aperture, the electromagnetic field will start to radiate quite well at the resonance frequency of those cavities. Okay, so you can use resonators to design broadband filter. As we say, we use this as a very simple filter. In the radio case, you can also concatenate the few of them together, making a broadband filter if you want to. So in microwave engineering, usually we concatenate a few of these resonators together to make microwave filters. And here's an example where you can concatenate a few resonators together so as to make a broader band filter. And you can also make optical filters. Making optical component is quite difficult, so you have to make them quite large compared to wavelengths. And a Fabry-Perot resonator, which is expressed here, a Fabry-Perot resonator. It's just a resonator made of a thin dielectric slab, and then as you hit the resonance frequency of this, the thin dielectric slab, due to resonance tunneling is the effect that you come across quite readily, then the electromagnetic wave can tunnel through this structure quite easily at the resonance frequency. So transmissivity is close to 1, close to the resonance tunneling frequencies of this structure. Okay. And because of that, you can use resonators to build microwave devices like this klystron here that amplifies microwave signals. Say if you have a microwave cavity here, you inject microwave energy into it so as to produce some low-level energy of microwave here, and you have an electron beam that has a lot of kinetic energy. The microwave will pick up kinetic energy from the electron, and as it rides on the electron beam, it becomes stronger and stronger. And then you have the catcher cavity, which catches the microwave emission from this cavity, and then it can be actually taken out to be a stronger microwave signals. These are very simple klystron microwave amplifiers. And you can also make amplifiers in lasers where you have saturation, population inversion thing. I'm not going to go through the physics of this, and I'm sure that many of you know about this, that you pump the molecules or atoms in your laser to be in the upper level. And when all the states, all the molecules in the upper level drop to the lower level, they have to give out photons. And those photons can be made coherent by enclosing them between two resonator walls. Okay. And you can also make semiconductor laser diodes. Making this semiconductor laser diodes is actually quite difficult at room temperature because you have to have both electron hole pair carrier together with the photons acting very closely with respect to each other. And if you have them acting very closely with respect to each other, then you can have energy transfer from the electron hole pair to the lasers, making this into a semiconductor laser. And that is actually a big invention in our technology area. And the person who did that actually were given Nobel Prizes for doing that. You can also use cavities to measure microwave because you can send microwave through a cavity. As you've seen here, you can adjust the size of the cavity. And if the cavity frequency agrees with the microwave frequency, it will start to build up very strong electromagnetic field here. And the electromagnetic field will dissipate energies into the walls of this cavity, showing that it is siphoning off energy from this input area. And then you can know that, well, the cavity size must be coincide with the resonant frequency or the operating frequency of the power in. Okay, so those are some of the early things that we learned about resonators. Then we talk about the Q of a resonator. The Q of the resonator, you can actually understand by studying an LC tank circuit. If you have a pure LC tank circuit with no loss, the oscillation in this circuit will last forever. However, if you put in some loss, then the oscillation would have to decay with respect to time. And you can actually work out the resonant frequency in circuit theory quite easily. And in the case of a lossy cavity, then the energy or the voltage in the cavity must behave something like that. Okay, it will have to have the time decay, something like that. And if you use this concept, you can easily show that energy being proportional to voltage square and loss being proportional to something causing it to decay with respect to time. You will find that the Q of the cavity, which is representing the number of cycles the cavity can go through before it decays to 1 over E of its original value. This number of cycles in radians is the Q of the cavity, and is given by this formula over here. And this sort of illustrates what happens if you know the Q of the cavity. The higher the Q, the sharper is this resonance point, and is somewhat related to the half power bandwidth of the circuit system. And then you can use this to define the Q of a resonator. And in order to find the Q of the resonator, you have to estimate the power dissipation. And you can find that the power dissipation is given by something of this nature, and then the total energy stored is given to be something of this nature. And you find that this formula can be written as omega times the energy stored divided by the power dissipation. So if you have a way to calculate the numerator and the denominator, then you have a way of estimating the Q of the cavity. Okay, so the Q of the cavity is also very much related to the location of the pole in the complex plane. And this plot just shows that if you know where the pole is located, you can find alpha, you can find the bandwidth omega 0, the operating frequency, and from that you can easily estimate the Q of the cavity. And you can use this concept to estimate the Q of a microwave cavity by estimating the wall loss. Okay, you use Poynting's theorem to estimate the wall loss on this cavity surface, and you make the approximation that near the cavity surface you have something that resembles a plane wave. And if you have something that resembles the plane wave, then you can actually show that the wall loss is actually proportional to E cross H, and then the E and the H can be found using this very simple formula on the wall of the cavity. And then you can find the stored energy, and that stored energy together with the wall loss calculated in this manner allows you to find the Q of the resonator. Okay. Then we talk about orthogonality. Orthogonality of waveguide modes and cavity modes are very, very similar to the orthogonality of eigenvalues and eigenvectors in the matrix problem. Here I just proved that they're actually homomorphic to each other. So if you have a waveguide problem, for instance, which is this one over here, you can think of this as an eigenvalue problem where this is a matrix operator, this being a vector, and this being the eigenvalue, and this being the vector again. And then you can show that A is Hermitian, so is this operator is Hermitian, that all the eigenvalues are real, and they're also orthogonal, which I'm not going to prove in this lecture. And let me go on to lecture 23. Okay, lecture 23 is on scalar and vector potentials. How do we calculate radiation fields and so on? And So here is an example of a movie of a Hertzian dipole radiating. You can see that this thing is changing its polarity back and forth. Eventually, due to the finite velocity of light or electromagnetic wave, the field cannot keep up with the changing sign of the source. Eventually, they have to tear off from the source and radiate away. That essentially is the physics behind radiation. So we have actually solved Maxwell's equations in static before using scalar potential approach. And these are the things that we had to go through using scalar potential. We use the fact that divergence of B has to be 0, then B has to be proportional to the curl of something. So we obtained these static equations in the past. But what is more interesting is that we now have to apply this scalar and vector potential approach to electrodynamics. Okay, so this is not true anymore. Curl of E is not equal to 0. So we have this equation still been there, but this equation is still true. The third equation, so you use mu H equals curl of A, and then you plug H being related to A into this equation. And if you go to the math, you find that the electric field has to be proportional to the gradient of the scalar potential times j omega A times A. Okay, so you have to augment this term with this term, which we usually call the induction term. It comes about is because the electric field is coupled to the magnetic field. Okay, and now if you plug into Maxwell's equations, making sure that the other Maxwell's equations are satisfied, then you would arrive at actually two rather important equations that the vector potential and the scalar potential satisfy these two Helmholtz wave equations. Okay, you have Helmholtz wave equations driven by sources. Okay, and those are important equations, and we know how to solve them using the Green's functions method, because the first equation is just three scalar wave. Even though this is vector, it actually consists of three scalar Helmholtz wave equations together, and you can apply the Green's function technique for each of the component of the vector Helmholtz wave equation. And then if you know how to solve this equation with a point source on the right-hand side, and we have done this for static problems where beta equal to 0, we found the Green's function to be this. But in one of your homeworks or take-home exam, you have been able to prove that the Green's function is this for this Helmholtz wave equation over here. Then you can use the principle of linear superposition to solve these equations and obtain them as your as the solutions to the two equations that we have. Okay, so these equations can be solved easily in terms of these integrals, and it's also a common practice to add fictitious magnetic current and fictitious magnetic charges to Maxwell's equations to make them symmetrical. And for the fictitious magnetic current, this kind of charge continuity equations will have to be satisfied. And then in order to solve this problem, you can solve it as a linear time invariant system where in the first instance, you turn off the magnetic sources. Okay, turn off these magnetic sources and then look for the output. In the second instance, you turn off the electric sources, okay, and look for the output. And you can actually get these two solutions by using duality principle. And having found these two cases, you can use the principle of linear superposition to find a solution when you have both M, rho M, J, rho E all turned on at the same time. Okay, so the next question we ask is, we have studied electrostatic theory, and now we are into electrodynamic theory. Electrodynamic theory is more complicated. Okay, we would like to know when we can use this simpler form. Since a Helmholtz wave equation, these are just Poisson's equations, which are a lot simpler to solve. And you can actually do dimensional analysis and find that you can ignore this term when Laplacian square is important or is dominant. That makes Laplacian square dominant in the near field. That is, if you're close to an object, the electromagnetic field have to become contortionists, and they have contort themselves to satisfy the boundary conditions. Hence, the E field and the H field has to vary on the length scale of L, which means that your partial X, partial Y, partial Z have all to vary on the length scale of 1 over L. If you use that dimensional analysis argument, you can see that this term, which is proportional to Laplacian square or partial square, partial X square, would be proportional to 1 over length square. Okay, whereas this term is proportional to 2 pi over lambda square. So if you compare the size of these two terms, if the size of the object is much less than the wavelength, then we can actually drop these two terms and replace your theory with electrostatic theory. It's written up more carefully in the lecture notes, which means that even in optics, when the frequency is very, very high, 10 to the 6 cycles per second or hertz per second, the wavelength is about 400 nanometers. So you can see that when we have a nanoparticle, which is about 10 nanometer, you can still use electrostatic analysis to analyze the interaction of light wave with these nanoparticles. And then you find that the solutions can be sought using electrostatic theory, and these are your solutions. The only interesting thing is that this epsilon of plasma, if these spheres are made of plasma, they can be negative. They can be negative in such a way that, let me see. Yeah, epsilon S is the epsilon of the particle. They can be negative. And when they're negative, these two terms can cancel each other. Okay, when they cancel each other, then this thing goes to infinity. And that's when you hit plasmonic resonances. And you can use this to actually change the reflected light from a cluster of nanoparticles immersed in fluid with different epsilon. If you put the fluid to have different epsilons in the background, this resonant frequency will occur at different frequencies, and hence different light ray or light wave of different spectrum will be reflected, giving you a rich sample of colors. Okay, so here is just something to show that even though in circuit theory we try to throw out the term that involves displacement current, and we also try to throw out the terms that involve the induction term or the dB/dt term in Faraday's law. We can make devices to emphasize them. Like the capacitor would try to emphasize the displacement current, and then the inductors would try to emphasize the magnetic flux linkage term, making all the four terms and every terms in Maxwell's equations to be important, even in circuit theory. So in a sense, circuit theory is wonderful. You have not actually thrown out anything, and you have all the physics of electromagnetic theory being embedded in these devices because of how we engineered them. Okay, so let's go to lecture 24. Actually, I'm kind of running out of time. So what we do here is actually to revisit circuit theory and find out what happens. And the message to take home is that circuit theory is important. You can actually emphasize the induction effect and the displacement current effect by using special devices, capacitors and inductors, to bring out those terms like this term in Faraday's law, and then to bring out the displacement current term in Ampere's law. Okay, so everything is there. Actually, you did not throw out anything important. Okay, in essence, what I want to emphasize is that by clever engineering, these terms are kept in circuit theory. Okay, and you kept them to be non-zero with inductance and capacitance. So circuit theory is very rich, and it has been driving our electronic packaging industry, computer chip industry for a few decades now, okay, because of clever engineering. You can see that these are some of the things that you have inside the computer chip. You can model this nanometer size devices now using circuit theory. And then now you have a very important software called SPICE. Because of microwave engineering, because of the increasing frequency of operations of circuit devices, you even have to use Smith charts to understand what happens inside a computer chip these days. Okay, let's go to 25. Okay, I'm running out of time. And 25 is the radiation due to a dipole. Okay, Hertzian dipole and so on. Okay, and then you can read about the physics quite easily. But the important thing is the math. Okay, when you plug in a point source current into the math, you get a closed form solution for the vector potential. And from that, you can derive your near field and far field. You can exactly derive the magnetic field and the electric field, both for near field and far field. Then the next thing to do is to elucidate the physics to see what we can do about this very complicated mathematical expression by taking limits. So in order to gain insight, we take limits by assuming that we are very far away in terms of wavelength, which means that beta R is much, much larger than 1. And it has to be remembered that the yardstick in electromagnetic is the wavelength. When they say something is large, it's large compared to wavelength. When something is large compared to wavelength, it says that this thing is large, and then you can go to those mathematical expressions and figure out that in the far field, they simplify to something relatively simple. This looks like spherical waves. Okay, that's one thing. And then spherical waves start to look like plane wave. And if you compare the two components of the theta and the phi component of this spherical wave, they actually look like plane waves. So in the far field, the E and H field look like plane wave. Okay, and you can actually, because of the fact that they look like plane wave, you can look at the complex Poynting vector, and then the time average instantaneous Poynting vector is half the real part of the complex Poynting vector. You can easily show that if you take the half the real part of this, it corresponds to the time average instantaneous Poynting vector. And then you can work this out mathematically quite easily. And you can also find the far field power quite easily, and then you can define something called the gain pattern or the gain function. Or for the Hertzian dipole is something very simple. You can define something called the directivity, which is the maximum value of the gain function. Okay, and then you can actually plot these things quite easily. Okay, and then another part is engineering. How can we engineer antennas so that all the power of the antenna goes in the preferred direction? That is called antenna array design. Another thing is that if you were to find the radiation of a dipole antenna, the radiation of this dipole antenna, the current distribution actually looks something like this. It has to be 0 at both ends. And because it's been fed from the center by a source, it has to be non-zero at this thing. But when you perform the integral, radiation integral, only the effective areas under this triangle matters. So you can replace this with an effective area of a short dipole, which is half its length, which is A/4 instead of A/2. And then you can calculate the radiation pattern quite easily. And that is actually what happens in a half-wave dipole. The current is not a constant because this actually looks like a transmission line. And then you can calculate the radiation pattern by going through a lot of mathematics. Okay, let me go through the next slide to see what is important. Okay, again, when you calculate the far field, you will have to make approximations. So these integrals are extremely complicated to calculate. They're pretty useless in their present form unless you have a computer. So in olden days, people don't have computers, but they're clever. So they're going to make what is known as the far field approximation. Okay. For the Hertzian dipole case, it's simple because these are point sources. But for other sources, where you cannot make a point source approximation, you have to do something cleverer. Then what you do there is to make approximation in the exponential term, okay, which is this term over here. Okay, if you can make some approximations in the exponential terms, maybe these integrals are still viable. So that's what people do here, which is that if you have something in the exponent, can we make an approximation on r minus r prime? You can actually go through the math and show that r minus r prime can be approximated by this thing on the right-hand side. That is called the parallax approximation and the far field approximation. And then if you do that, then you can show that the far field vector potential can be approximated by this integral, and you can further approximate it and show that the far field vector potential is proportional to e to the j beta r, which is independent of r prime, times this integral, which looks like a Fourier transform. So you can see that the far field of a source is proportional to its Fourier transform. That's something that you should keep in mind, something that you should be having this tucked away so that the far field of any current is proportional to its Fourier transform. Okay, and then here are more things about Fourier transforms. And then when you are far enough from the source, you have something that looks like a plane wave locally, so you can do local plane wave approximations. And you can actually look at these far fields. They have actually plane wave-like relationship between them, called the local plane wave approximations. And then you can look at the complex Poynting vector because they look like plane wave. You can also look at the instantaneous Poynting vector. Then there will be a relationship between this complex Poynting vector and the instantaneous Poynting vector. And you find that because they're like plane wave, their far field has a complex Poynting vector that looks something like this. Okay, you can work that out, and then you can look for an average radiative power, which is the total power divided by 4 pi r squared, assuming that the radiation is isotropic. Then you can define a gain function, which is the far field power pattern divided by this average. Okay, and then you can also define the concept of an effective aperture. Effective aperture is something that you put in space that when it intercepts an incident power, this incident power is in terms of watts per meter square times meter square, give you the power received. And it turns out that the effective aperture of an antenna is given by this lambda square over 4 pi times the gain function. Okay, this is entirely the property of the antenna you design. This is effective aperture, and they are related by this universal constant lambda square over 4 pi. Okay, here are just some examples of antennas that you can design. Let me go to this lecture by Dr. Dong Yap Na. He prepares this beautiful lecture notes. When you have a Hertzian dipole antenna, it essentially radiates like a donut. It does not radiate in the axial direction, okay, but it radiates predominantly in the broadside direction. And you can use this for 5G communication. The thing about 5G is that they're using some pretty high frequency there. And in those frequency range, the wavelength is on the order of millimeters. So these are also known as millimeter waves. And they're good because it can carry extremely broad bandwidth and lots of data. And you can actually communicate in an urban environment in a very fancy way using 5G communications. And of course, you can have base stations, antennas, and they will have different operating frequency. I'm not going to talk about this very much. Okay, so what we have to do then is your ability to calculate the far field by an array of dipole antennas. Okay, so we did that, and once you have an array of dipole, after having made the far field approximation, they're just related by Fourier transform relationship. And then if you put this array of dipoles together, it turns out that the mathematics is viable. You can actually sum these terms. And once you sum those terms, you can have a simplified expression that looks beautiful, and it just looks very simple. And if you work with this some more, if you take its magnitude, you can simplify this into what is called the digital sinc function. The digital sinc function will have something like this, but it repeats itself. Okay, there's a difference about the digital sinc function. And then from that, you can plot antenna patterns of this array. You can define the phase between the arrays and the number of elements. You can come up with a rich variety of radiation patterns that you can have. Okay, and then you have this concept of near field. Okay, Fresnel zone and the far field. The Fresnel zone is somewhere between the near field and the far zone. Okay, and before you reach the far field, you cannot use a far field approximation. Only in this regime can you use the far field approximation. You have to be larger than this distance. So if your antenna array is very large, you have to go even further. Okay, you have to go even further to reach this zone over here. That is called the Rayleigh distance. Because the Rayleigh distance is the distance beyond which you can make the far field approximations. Okay, and let me see if I have yeah, this lecture is full of beautiful graphics because I essentially describe everything heuristically. I did not do a lot of mathematics, but I hope you get the point. In order to understand the physics of the antenna design, you have to understand the heuristics and the physics behind them. You run commercial software to zoom into the correct design. Okay, now antenna design is driven by commercial software. Then let me go into different types of antennas. I think we did that already. Oh no, I opened the wrong slide. Okay, I should go to lecture 29. Then we talked about uniqueness principle. Okay, uniqueness theorem, which is something that we just recently covered. We want to know what kind of boundary conditions would guarantee uniqueness. And if it does not guarantee uniqueness, what do we have to do to get uniqueness? So the take-home message for this lecture is that you have to specify tangential E on the cavity wall or the surface of the zone, or you have to specify tangential H on the wall of this surrounding surface S. And sometimes you still have non-uniqueness problem, then you have to put in some laws. Okay, you have to put in a little bit of laws in order to prove uniqueness. Okay, we show that finally, if you put in some laws, uniqueness is guaranteed because you arrive at this equation, and this equation can only be zero if delta H is zero or delta E are both zeros. Okay. Then the anisotropic case, I was only discussing them in the lecture notes, so I didn't discuss them. And non-uniqueness is very much similar to the existence of null space in the matrix problem, if you have a matrix problem to solve, if the matrix A has a null space, then the solution is not unique. And this is actually very similar to that. Okay. And then you have the problem of radiation. If you have a lossless region, how can we guarantee uniqueness? As I said before, you can introduce a little bit of loss to guarantee uniqueness. And that is the same as requiring that the field goes to infinity and never to come back. And it's the same as requiring an outgoing wave that travels to infinity only. Okay, so you can actually go through the thought processes of what actually happens when you put the point source in the cavity, and the chance that you hit a resonance solution is very high as you make the cavity bigger and bigger. But if you put in a bit of loss, then uniqueness would be guaranteed, okay, as we usually do by assuming a little bit of loss in the region. And then, as you have seen in solving this Green's function problem, the solution is not unique. And we only kept one of the two terms by a physical argument, by saying that I can only tolerate the existence of the outgoing wave, not the incoming wave. It strikes out to be zero, then the solution becomes unique. Okay, so that is uniqueness principle. And then let's see what next. The next thing that we talked about then is, let me see, is reciprocity. Reciprocity is like human relationship. If you're good to me, I'll be good to you. If you're bad to me, I will strike back. Okay, that is reciprocity principle. And Confucius knew that over 2,000 years ago. So did Jesus Christ and the Old Testament, not the Old Testament, the New Testament. Okay, so you can prove this precisely using mathematics. In electromagnetic theory, you do experiments involving two sets of sources. Okay, you can actually go through the proof. Okay, and the proof is quite involved. And if you guarantee, if you assume that mu is symmetric, epsilon is symmetric, then you have reciprocity theorem of the first kind called the Lorentz reciprocity theorem, which says that these two integrals have to evaluate to zero. And then if you assume that the surface S encloses the sources only, and then you can make the surface S goes to infinity, then the reciprocity theorem reduces to these other ones over here, which you can write in terms of reaction, the reaction between two kinds of sources in the two experiments, okay? And then we introduce a concept of inner product. Inner product in Hilbert space is actually very similar to inner product in linear algebra space, okay? And then you can use this reciprocity theorem to derive something very important in circuit theory, which says that if you have a reciprocal circuit, then this matrix has to be symmetric. And so because the matrix is symmetric, reciprocity applies, then you can do a lot of wonderful things. This is just to point out the fact that when you have a gyrotropic medium, the tensor looks something like this. It is not a symmetric tensor anymore. So a gyrotropic medium is not a reciprocal medium. And here I just showed that reciprocity is very much deeply related to the symmetry of the systems of equations that you're involved with. And then you can also use reciprocity to prove that the transmit function and the receive function of an antenna are the same. They are actually governed by the same function, okay? And then we just have this last lecture that we had, which is on equivalence theorem. Okay, you have to do Duncan experiments to understand this equivalence theorem. And then you can prove them by thought experiments, which is the first part of the lecture notes. Okay, and you can conduct a sequence of thought experiments and argue that these are equivalent problems. But if you don't like to conduct thought experiments, you can also do it mathematically, which is something that we try to do here. We write down the solutions in both regions for the scalar wave case using Green's function, and then you very easily show that you can come up with a mathematical relationship, and then you can form a kind of relationship between the field and the sources on the surface, and that would be very much like what we found in the thought experiment case, but that was for scalar wave. Scalar wave, the mathematics was simpler. Then you can repeat the same for electromagnetic wave, where the mathematics is harder because you have to work with vector wave equations, and these vector wave equations are a bear to work with because you have to worry about their locations, their orders, and a lot of other things. But it's written out in the lecture notes very carefully. So you can read the lecture notes, you should be able to derive some of this equivalence theorem or Huygens principle mathematically as well. I'll stop here unless you have any questions. Are there any questions? Any questions?
No for me, Professor.
Okay, very good. I don't know if this mode of review is good because I tried to cover all the previous lectures. Maybe next time, if I don't have enough time, I can pick out a few topics to cover. Okay, so I'll let you go and thank you for coming, and take good care of yourself. It's still dangerous out there. Okay.